Okay, so I'd like first to thank the organizers of this workshop for inviting me to present this work. All right, so my name is Gustavo Carneiro. I'm the Director of Medical Machine Learning and an Australian Research Council Feature Fellow at the Australian Institute for Machine Learning at the University of Adelaide in Australia. And the title of my talk is Anomaly Detection and Localization in Medical Image Analysis. And this is work in collaboration with Yu Tian, Fengbei Liu, Yuanhong Chen, Yuyuan Liu, and Dr. Ming Song Tu. So before I get started, let me first introduce the problem of anomaly detection. So anomaly detection is the problem of detecting outliers or novelty in a distribution. And the idea here is that you want to identify samples that deviate from a normal distribution of samples. And normal here usually means sample from a healthy population. So for example, if you have this space with 2 dimensions and the normal samples are distributed like this, the goal then is to learn something about this distribution and perhaps using only samples from a normal distribution, such that when there's a sample from an anomaly individual, right? So an anomalous sample, you're able to identify because it will be sitting in a very different place from where the normal samples are distributed. So then the goal is to learn a model that can separate the normal from anomalous samples, even if these anomalous samples are not available for training. So, there's a lot of different types of anomaly detection systems, but there is usually this division between methods that can learn using only normal samples. I will talk about it, and methods that can learn with, the majority of samples from normal population and just very few samples from a normal population. So the motivation is very clear, particularly for medical image analysis. Some data sets, particularly in screening problems, the data sets will contain a disproportionately large number of normal cases. So just a screening problem is problems where you are just trying to scan the whole population with the goal of detecting particular diseases. And in general, you're trying to detect cancer, right? And you just try to do early detection of cancer using the whole population. So because the whole population will have a very small percentage of samples containing cancer, naturally you have a disproportionately large number of normal cases. And you will have a quite small number of abnormal cases. In the case of cancer detection, you have a very small percentage of population with cancer. And typical examples of data sets here are colonoscopy, that you see here on the left, mammography, that's this one in the middle, and fundus, that's this one on the right-hand side. And for the colonoscopy and mammography, you're trying to detect early signs of cancer, right? So you're trying to detect lesions. Colonoscopy, you're trying to detect polyps. In mammography, trying to detect masses and microcalcifications, for example. And the fundus image, you're trying to detect many different diseases. So the advantages of using anomaly detection in medical image analysis is that a lot of the systems that we have can use only normal images for training, which means that you can have very large training sets. And one particular advantage is that you can actually use a small amount of annotated abnormal cases. In this case, that we usually call this a few-shot anomaly detection. And another big advantage is that you don't need to have all possible types of anomalies to be able to train, for example, a few-shot anomaly detection, or might as well not have any anomalous sample at all. But the system should be able to adapt to any new types of anomalies that are not present in the training set. Of course, the challenges are, so first one, robustness to any type of a new anomaly, right? So in the case that you have a training set containing only normal samples, you obviously have to be robust to any type of anomaly that happens in the test set. And that's usually very challenging depending on the type of anomaly you're looking for, or that is presented to you in the test image. And that's particularly difficult when the anomaly occupies a very small area of the image. So in this example here, you see colonoscopy image with this very small polyp. And that's true for the other images that I showed before in mammography, for example, with small lesions. And that's a very challenge because trying to get these small regions in the image, and the whole image looks pretty much normal compared to the normal population, becomes really challenging. You can also have extremely imbalanced data sets in the case of few shot anomaly detection. So here we're talking about, maybe 10,000, 100,000 normal samples, and then you can have just about 100 anomalous samples, and that huge imbalance will cause problems, obviously, for training. Another issue is that separating anomaly versus rare samples that are not anomalous is also very challenging. So a good example here is in colonoscopy, that you have water jet. During the colonoscopy, the doctor sometimes will put a jet of water to clean up the bowel, such that the doctor can see better what's going on. And that creates this image here that looks nothing like what a normal image looks like. And also feces also can create problems, during, the detection of anomaly, because sometimes, an image like this may really look like an anomaly, much more than an image that has a small polyp like this, right? And if you don't have this in your training or somehow reject these images, you will have a lot of trouble, a lot of false detections. While, you have a polyp here that doesn't look exactly like that, but in the same way, it looks very anomalous, right, compared to what a normal image should look like. So there are many ways to solve anomaly detection, and I would talk about two ways, which are the ways that I usually used to solve the problems that we'll talk next. So one particular technique, and it's been used up until today, and it was proposed in 2001, is the one-class classifiers. In this problem, what you try to do is you try to take the normal samples that you see here, and you try to learn two things. One is you try to minimize the radius of the distribution of the sample. So imagine you have a sphere that would be around the samples, and then you try to minimize the radius of this sphere such that the samples will get closer and closer together. And at the same time, you also want to learn the parameters of these features. So, it's like two ways to put all the normal features together in a particular region of the feature space that is centered at this C center. And then during the test, what you expect to have is that, an anomaly will just sit very far from the normal samples that you see here. And then the classifier, which is basically, if it's within some radius of this center, we'll just tell, well, this is just sitting too far away from the normal samples. And then you're able to detect the anomaly. So it's like a classifier that detects anomalies. However, the end-to-end learning of feature and the classifier is quite challenging in this setup. So another method that is very explored in the field is this generative model plus reconstruction loss. So let me explain this in part. So the generative model here would be, for example, an autoencoder where you have an image in the input that is encoded to some embedding, and then that's decoded to some image again, and then you try to do this reconstruction loss like you do normally in autoencoders. And then you also train a discriminator here that would discriminate between the reconstructed image and the original image. And then that discrimination would just tell that this is real or reconstruction, right? So the hope here is that the autoencoder can only reconstruct your normal instances, because during training, you only present the normal images to this whole training. And when you present with an image that contains, in this case, a polyp or a lesion or something, an anomaly, then the whole reconstruction will be very confused, and it will reconstruct something that doesn't look like the input image, such that it looks like an image that could fool the discriminator into believing that this is a normal image, right? However, there is a big problem with this method here, which is that it tends to reconstruct really well input images, well that if it contains small anomalies, we'll just reconstruct the anomaly, which is bad, right? Because that's exactly the thing that we are trying to detect. Right. So the first method that we tried to propose, that we proposed actually a couple of years ago to address this problem is the ADGAN, where our main contribution is that we use this dual generator discriminator, one to generate images and another one to generate latent vectors. And then you have this cycle loss here that's, you take an image, put through the, we have a discriminator that discriminates between real images and generated images. And then you have latent variables that would generate an image, and then it goes through the latent generator, from the image to the latent generator. And then you have a latent discriminator that would discriminate between the latent generator and the random latent variable. So the goal here was to constrain the latent variables and such that the whole training of the methods is very well constrained. And then during testing, you would take an input image, go through the latent generator, and then go back to the visual generator to produce an output image. And then the anomaly score would be based on the difference between the output and the input image. If the difference is too big, then that means this is an anomalous image. Right. So for the result, we had our own data set of about 30 colonoscopy videos, where from those videos, we have a training set of about 13,000 normal colonoscopy frames, where we exclude consecutive frames with feces and water, and blurry frames. So remember that those are the frames that look very different from a normal image. So we decided to exclude them because we need to have systems that could exclude them automatically, and we didn't implement this at the time. And the testing set would contain 219 abnormal images and about 617 normal images. And then, and this is, the training contains only normal, and the testing contains normal and abnormal. And then we take our system and compared with some other systems that have been proposed for the same task. And our result is about 3% better than the best one that we saw that was available at the time. So it's interesting to see some of the visual results here. You see here on the top, you see the original images with the polyp, with this highlighted by this red silhouette. And then what you see at the bottom is the reconstruction of the polyp. And as we predicted, the system got in trouble reconstructing polyps, right? So you see this polyp here, and then you don't see that polyp there. Similar here, see a big polyp and no polyp there, and so on. So which means that our assumption that the system gets in trouble reconstructing polyps is true. And it's, what was very exciting is that the system was actually able to not reconstruct small polyps like this one on the right-hand side. So you don't see the polyp here while you see the polyp in the original image. So we extended the system with a few-shot anomaly detector. So in this case, we assume that we have available, a few images that look that have some anomalies in that in the image. And the whole point of this system was to build a classifier for the anomaly, which is represented by this score inference network that you see here with an anomaly score. But the main contribution of this work is the pre-training process. So what we have here is normal image that goes through the encoder, and the pre-training would have 3 losses. 2 of those are based on the deep infomax work. So basically, this is unsupervised pre-training. And then one of those is a prior discriminator that tries to pull all the normal images to the center of the normal images, which we assume to be 0. So that's why I see here that pulls the embedding of normal images to Gaussian mode at 0. And after you do the split training using only normal images, you take the encoder and then you give some normal images, a few shots of normal images, and then you train the score inference network, which is trained with a loss that is very similar to a contrasted loss to produce an anomaly score. So basically, you're trying to put all the normal images together in this mode at 0, and all the anomalous images far away from 0. So that's basically what this loss is doing. So using the same data set as before, but including from 10 to 80 abnormal frames, and same test set. So we compare our results with zero-shot anomaly detection. So this is what you just saw before, this first part of the table. The second part is a few shot, where we basically compare with different methods like DenseNet or just cross entropy, focal loss. And then what we're trying to do is to see, for example, if our pre-training works better than the autoencoder, and it works significantly better. And if it works better than if you just have a system trained with few shot anomaly detection, where we have a very large training set with normal, very small training set with abnormal, and then we train a DenseNet, for example. And in both cases, our result is much better. More recently, we have proposed a general pre-training for anomaly detection. So basically, before we tried this deep InfoMax, and now we tried this, like the SIM-CLR type of training, where we have a contrastive loss, to train using only normal images. And then we also added two pretext tasks, one based on augmentation prediction and one based on patch location prediction. So basically what we're trying to do is we take an image here, we have a strong augmentation and a weak augmentation, and then we use the contrastive loss to put together the weak augmentation, push apart the strong augmentation, and at the same time we try to predict the strong augmentation, and also we try to predict this jigsaw puzzle. So we have these three types of losses to do just a pre-training using only normal images, and then we take this and we train both an anomaly detection and an anomaly detection and anomaly localization, as you can see here at the bottom. So we can do both. And so the detection and localization are based on systems that have been proposed before, like IGD and FN again. And for this work, we actually tried 3 different data sets. The hypervisor, which is a colonoscopy, it's a public colonoscopy data set with about 2,000 images, 1,600 for training, 500 for testing, and 1,000 abnormal images for testing. We used the same data set as before with 13,000 images, with 290 abnormal, 677 normal for testing. And then we also use the lag, which is the fundus images, with about 2,000 normal images for training, 800 normal, 1,700 abnormal. And compare our results to previous zero-shot or one-class classifier-based anomaly detection. Our method works better than anything that has been proposed before, as you can see from these results. So our result here with IGD is better, by a fair amount. And an interesting thing is this, right? So even though we didn't actually train for localization, and we don't even have annotations for that, the system is actually able to detect and to localize the anomalies on the image. So for example, we have here the image on the left-hand side and the prediction from the system, and this is the ground truth. Similarly, this image here at the bottom, you see the image with the prediction and the ground truth. So very close to the ground truth. And for MICAI this year, we also have this targeted pre-training. So here, our goal was to do a pre-training, but differently from before, where we didn't try to have a pre-training that is very targeted to the problem. So we tried a very general pre-training with SIM-CLR type data augmentation. Here we actually design a pre-training that is similar to the stuff that we will be looking for in the test images, right? So again, the training contains only normal images, so we had to kind of make up what an anomaly looks like. In this case, we're looking for lesion changes in multiple sclerosis images, and we only have normal images. So the way we decided to implement this lesion change detection was using a reconstruction from a VAE, and then using a superpixel to mix up superpixels from the reconstructed image and the real image. And what you can see here is the VAE reconstruction, the real image, and what you see in red are the superpixels that are passed from the VAE to the original image. So for example, if you see this big red thing here on the normal image, you'll see that the real image didn't have this region, and then it showed up with a region here that comes from this VAE. And we call this data augmentation supermix, sorry. So in terms of result, we used our private longitudinal volumetric to do T2 flare examinations with about 200 pairs of normal scans for training and 94 pairs of scans containing lesion changes for testing. So again, only normal images for training. And then for testing, we use only images that contain some type of lesion changes. And what you see here highlighted, the Siamese UNet is the result from our system in terms of true positive and false positive. And in all cases, we are getting better results than the current kind of state-of-the-art result. But this is a system that runs on several systems to detect things similar to lesion changes in this type of images. All right, so one thing that is interesting to see here is the visual results, right? So what you see here, this slide is 2 time points where you see the lesion changes, and what you see in blue is the actual annotation for the lesion change. So for example, in this first image here on the top left, so no lesion here in time point 1, and then you see a lesion here at time point 2. So that's why you see the annotation here in blue. And what you see in red is the detection from the system. So similarly, you know, for these 2 images here, the top middle, what you see is this lesion here kind of increasing a little bit, and then you see here the annotation in blue and the detection in red. And you can see similar things happening in all the images. You know, the system is, you know, quite effective at detecting these lesion changes. Right. So in terms of conclusions, I believe, you know, after working with anomaly detection for the last 3 years or so, 2 or 3 years, the best methods, they combine anomaly classifier plus generative and reconstruction methods and pre-training. So you need all these components to have a system that works reasonably well. The pre-training seems to be particularly important. And right now we have these systems that work with general pre-training, you know, using things similar to SIM-CLR and so on, or targeted, where you have to figure out good ways of making up, you know, the things that the anomalies that you're looking for. And both have their own challenges, as you can expect. And few-shot anomaly detection always perform better than one classifier, right? So which is expected, right? So once you have few shots of anomaly, then it makes the training a lot easier and your final results are a lot better. Okay, so thank you very much. And I will probably be available for questions later. Okay, thank you.